All right. So moving beyond the computer model of semantic memory store would be the associative network theories, recognizing that probably our brains are organized with a bunch of different neurons contributing different little details to a particular concept or idea. The associative network theory has this sort of messy looking, and this is a very simple network, but it gets messy really quick as you start to realize that different details would be directly related to each other. Some are not. They're only related through some other concept. It starts getting quite messy. So the idea with associative network theories is that there is an association. There are theoretical links between concepts. So in this particular diagram, liquor is the major concept. And then you've got details that are related to that concept, right? So the associative network theory makes the argument that there are these links between and among concepts. And some of them are probably stronger than others. Some of them are probably more direct than others. But the idea is that all of the knowledge that you hold is linked by associations of varying strengths. So here we have our little network that pertains to liquor. Maybe next to it would be a network that pertains to, weightlifting. And so you've got this concept up in the top left corner that says strong, that's probably attached to liquor and then is also attached to weightlifting, right? Like this is the same concept and it's probably activated by more than one network. And that's where that association comes in. That the information that you store in your memory is not a series of discrete little topics that don't get muddied up by other topics. The fact that you started to think about weightlifting and weightlifting makes you strong and some liquors are really strong, like that's how you end up with these weird, you've had these conversations where you started off talking to your friend about one thing. They said something else, you said something else. Next thing you're over here talking about something completely separate and you're like, how did we get here? Right? It was you guys kind of manifesting an associative network in real life, right? You're showing how ideas are linked to each other in probably some pretty loose associations, but that can lead you down a path of thinking about something completely separate from what you started off thinking about. So let's talk a little bit about ways to study whether there are these associative links between concepts. So back in 1968, Quillian developed this teachable language comprehender to test the idea of associations. The goal was to teach language to a computer. As a student, I always thought, okay, why don't we take the hardest behavior that humans can do, language, and try and teach it to a computer? Can't we start with something simpler like playing tic-tac-toe or something a little simpler? But okay, we're going to go right to language. All right. What they found is that using this teachable language comprehender, they were able to get the computer to draw inferences very much like humans do. When you're presented with an ambiguous word in spoken language, you have to draw inferences to figure out what the speaker might really mean. Actually, in written language, I encounter that a lot too. Sometimes you have a word that is spelled one way, but it can be pronounced two ways and mean two different things. Like, let's see, I'm trying to think of a good example. Like the word read is spelled the same way, whether it's present tense or past tense, right? Read or read, spelled the same way, but we have to draw an inference that they must have been doing it in the present or they must have been doing it in the past based on what else is going on in the sentence, right? Similarly, there are homonyms in spoken language where we say one sound and it could mean a lot of different things. I actually just had this experience with my daughter. She said something out loud, and from the context, I really couldn't narrow it down. We ultimately, as we laughed about the fact that I was confused by what she meant, I had it down to one of two things, and we realized there was actually a third definition of that same homophone word that sounds exactly the same, and it can mean three things, it turns out, and two were viable in the situation. You oftentimes notice as a human the inferences that you draw when you make the mistakes. When with computers, we notice that they're drawing inferences when they do it correctly, when they are able to figure out from context which of the words was meant and things like that. When they draw inferences, we're able to reveal that for these computers, they organize information in a hierarchical structure. So, for example, this is one way that Quillian kind of mapped out what it looked like the computer was doing. And so he thought, well, maybe this is what we do. So here we have at the top the concept of animal. The next layer are types of animals. So you got bird and you've got fish. And then below that, you have types of birds, canary and ostrich, and types of fish, shark and salmon. So this would be what we call a hierarchical conceptual organization. So you've got, animal at the top, like the most general at the top, the most specific at the bottom, right? He calls that most general one the superordinate category. He calls that middle range the subordinate category. And then at the bottom, all of those would be labeled coordinate to each other because they're at the same level as each other. There are multiples at the same level. All right. So hierarchical organization would provide what Quillian called cognitive economy. Like it would take less brain power, less space, less effort if we did organize things in this hierarchical way. Now over on our picture, you see I put this new label that says general assumptions apply to all lower levels. So if you see the superordinate category of animal has skin, can move around, eats and breathes, you can assume everything below it has all of those characteristics. So birds have skin, can move around, eat and breathe. Fish have skin, can move around, right? You don't need to repeat that at every level. And so that's economical, right? Just only say it at the top. Like everything below it, it's a given. So then we come down to bird, right? It has wings, can fly, and has feathers. And then you come down to the coordinate level and you see that canaries can sing. Canaries are yellow. Ostrich has long, thin legs, is tall, can't fly. Oh, look at that special case. It has wings and it has feathers, but it can't fly. Is this the most economical way to structure things? We'll talk about that more later, but let's just go with this for now. When you ask a person, does a canary have skin? According to what happened with the computers and also what we think happens with humans based on human behavior, it will take longer to acknowledge that a canary has skin than it would take to acknowledge that a canary is yellow. And why would that be? Well, when you go to access that information, does a canary have skin? You have to actually go first up to the bird level. Okay, that's not where skin information is housed. Then you go up to the animal. Oh, okay, yeah, I can confirm it has skin. So I had to go up 2 levels to access the information of whether a canary has skin. Whereas if I am going to answer, is a canary yellow? I can answer that question right there on the same level as the word canary. So the computers that were taught the language, that they showed that they were slower when making the judgment, does a canary have skin, than the judgment, is a canary yellow. Well, so do humans. It turns out that in experiments with humans, it takes longer to confirm that a canary has skin than it takes to confirm that a canary is yellow, implying that they do actually, that a human has to sort of go somewhere else to confirm that, or think at some deeper level, whether it's hierarchical or not, think at some other level to determine the answer to the skin question, whereas they can answer the yellow question right away. So that accessing information seems to be supported in the computer and in the human. So the assumptions of this associative network theory that was confirmed by the Teachable Language comprehender is that there is a category size effect. So if you have to go, if it's a larger category, it's going to be harder for you to confirm information about that category. It's going to take time. That all coordinates are equal. So you should be just as fast at confirming that a canary is yellow as you would be at confirming that an ostrich, is tall, or that a shark can bite, or that a salmon is edible. All of those, you would spend the same amount of time confirming those things. Now here we have the actual durations on humans. When they are in the bottom line there, you can see a canary is a canary very quickly. Mean reaction time in milliseconds. So 1,000 milliseconds is 1 second. So that's the amount of time it takes you to like see or hear the prompt and then push a button to to react. I mean, that's about as fast as you can go is 1 second. The next question up is a canary is a bird. Takes a little bit longer. So you go from 1,000 milliseconds to 1,200 milliseconds. And then a canary is an animal, a little additional time. So as you go up, right, a canary is a canary, that you're just making the assessment within the coordinate level. A canary is a bird, you had to go up to the next level, right? Up to the subordinate level. So a canary is a bird, you had to go up to the subordinate level to confirm that. When you're establishing that a canary is an animal, you had to go up to the superordinate category and establish that, yes, canary is an animal. And so now that's taking about 1,250. But now we start getting into some specific questions, right? A canary can sing. Okay, now that's going to take a little bit longer. Even though you're working at the coordinate level, it's going to take a little bit longer because you're like, okay, what is a characteristic of a canary, right? A canary can sing, okay, yes, about 1,300 milliseconds. A canary can fly, well, that's up at the bird level, right? That's up at that's up here at the subordinate level where a bird can fly, right? So canary can fly, okay, had to go up one level, so that slowed me down about 100 milliseconds. Canary has skin, had to go all the way up to the animal level, the superordinate level, and so we're up to almost 1,500 milliseconds to answer that. So we get that category size effect where it takes longer the more categories you have to go up. At the coordinate level, all coordinates are equal, and so a canary can sing should take the same amount of time as a shark can bite, and so on. All right. That seemed like that was a lot for you to process. So let's come back and talk about the spreading activation model in the next segment.